Okay, so we're grading 12.4, 12.4. But no one's gone today. Perfect. Period 4, I'll just say they're all here because they'll all be in their AP. I'll be checking out the Twitter feed from the East Coast kids to see what was on the test. Have to be ready when they come out. Depends on the kids. They were nervous, but they got their breakfast. They got their coffee. They were a little disorganized. We only had one calculator like almost blow up right before, but there was an extra one. Didn't blow up, but just like every time you hit the on, it would like pop and then disappear and pop and disappear. But someone had an extra one. That was good. Huh? Maggie did it for like 2 seconds, then Arian's like, here you go. She's like, oh, it's okay. Yeah, she put new batteries in, and she was like, it's not staying up. But it's all right. She figured it out during breakfast, so we figured it out. BC got their Burger King crowns. So it was good. All right, any odds? The vegetarians got their egg bake. That did not have meat. Corey Shower got his orange juice. All right, so it wasn't a bad section, yeah? So what was the whole section about? Limits to? Okay, the book might say at. It's still the same thing. And how do we take limits to or at infinity? The shortcut way? The degree tests. And what else did we ever use the degree tests on? Way before we ever learned limits? Horizontal asymptotes. Good job. All right. Section 12.5. For those of you guys that were gone yesterday, we briefly introduced this page. We basically said, hey, we've seen these before. But actually, before we even talked about that, we were like, oh, hey, remember there's 2 big problems of calculus that laid the foundation of calculus? One was a tangent line problem, section 12.3, how to find the slope at a point. Because for point-slope form, the 1 point that we have is enough, but the slope we're struggling on. And so then we realized, oh, hey, the slope of the tangent line is found using the limit as the distance between the points of a secant line go to 0 of the difference quotient, which is the exact same thing as, what's that snazzy word we learned in 12.3 that means the slope of the tangent line? It's the first semester of calculus. What is the term that we learned in 12.3 that signifies the slope of the tangent line? Its notation is f prime of x. It's the derivative. It's the derivative. Divergent and derivative are very different. So now in section 12.5, now that we've learned limits to or at infinity, now we can come to the area problem. We couldn't have done the area problem earlier because we need to go to infinity, and so we had to cover section 12.4 first. Let's see. This is the formula for the sum of an infinite geometric series as long as the geometric series does what? Converges. Good. So this will only exist as long as, we should say, an infinite convergent. And what does it take for a geometric series to be convergent? This right here. The common ratio has to be less than 1, or I should say the magnitude of the common ratio has to be less than 1, which means the common ratio has to be in between -1 and 1. And as long as that is true, we can come down here and say, hey, this what we would call an infinite series. I was about to call it something different. An infinite series would be found by the notation I already showed you guys way back when because I thought you could handle it. The limit as n goes to infinity of the summation of the geometric series, which means I take the limit as n goes to infinity of my formula, and only when the magnitude of r is less than 1 will this little r to the n component of the s sub n of a geometric series approach 0. And when it approaches 0, the infinite sum will exist and will be the formula that you have. Now that's all spiffy and good, but that's all review, technically. This page, not so much review. This page says, you know what, in order to be able to solve, To solve basic integration problems. Ooh, integration, that's a new word. Anyway, to solve basic area problems, we're going to need to know these basic summation properties. So, basic summation properties. Let me show you where some of these come from. Ready? This sum would be, well, plug in 1. There is no I, so it'd be C plus C plus C plus C plus C. How many times? I don't know, until you stop. So how many C's will there be? N. N times C. This one, if you were to go ahead and plug in, you would have A1 plus B1 plus A2 plus B2 plus A3 plus B3, etc., etc., etc. So this one, yes, we could keep it A1, B1, A2, B2, A3, B3, or we could just say A1, A2, A3, A4, all the A's, and then B1, B2, B3, B4, all the B's. That's where that property comes from. Otherwise, I guess we could show you one more that's pretty easy to understand. K times A1 plus K times A2 plus K times A3 plus K times A4. When you plug into a series, you're just going to have a sequence of terms that are being added together. And so what can we do if there's a common factor in all of them? We could factor it out. And that's what they do. They pull the K out and just deal with what's left. Now, the ones that are tricky, and I'm going to highlight them. The ones tricky that we need to know are these ones right here. And to be honest, I don't even totally have them memorized. I have to rememorize them every time. These ones are tricky. They're not quite as straightforward, not quite as common sense as the other ones that I was showing you. These ones are tricky. The sum of I squared, and the sum of I cubed. Bless you. If we were to get into more complicated functions, we would probably need the sum of I to the 4th and I to the 5th and I to the 6th, and sadly they would probably have their unique summation formulas. But we're only going to deal with I and I squared and I cubed. These are kind of just needing to memorize sorts of things. These are kind of just more needing to memorize, which for the final you can put it on your formula card, no big deal. But for Friday, okay, you better highlight those, okay? Especially those, I and I squared and I cubed. So the sum of I, and this one is the sum of 1 plus 2 plus 3 plus 4 plus 5 plus... Depending on where you stop, depending on what m is, I mean, it does technically kind of go back to an arithmetic series and how to find the nth partial sum. Go back to little Gauss in his super noisy classroom, and the poor teacher just wanted to break with the problem adding all the numbers 1 to 100. That's kind of the idea that's going on with number 2. But as soon as you have I squared, that trick goes out the window, because now you have, no, not 6, 3 squared is 9. Oh, that didn't work. Undo. 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 Okay. 1 plus 4 plus 9 plus 16 plus. And this one would be even worse, because this one would be 1 plus 8 plus 27 plus 64 plus... Ugh. So those ones, the patterns aren't near as nice as the other ones. And so we have these special formulas to keep us honest. If you look at it, this one, n times n plus 1 over 2. This one is n times n plus 1 all over 2 times an additional 2n plus 1 over 3. You can think of it like that. But then as soon as you get over here, you're like, wait a minute, what? And it just gets a little more complicated, because it's basically this times itself. So it's n times n plus 1 times n plus 1, and 2 times 2. Anyway, so what's the point of that? Like, what are we supposed to use it for? Well, if they wanted us to evaluate the sum from 1 to 200, I guess we could just add it all in our calculator. I guess we could try to do Gauss's trick of adding the 1 plus 200, 201, and realizing that we're going to multiply that by how many 201s are there going to be, guys? Do we not remember Gauss's? 1 plus 200 is 201. 2 plus 199 will be 201. 3 plus 198 will be 201, etc. We could use that trick. Let's see how that measures up, because that technically is one answer. Let's see how that measures up with the formula that we have on the page before. So the formula on the page before would say, okay, in order to add, in order to solve, we would need n times n plus 1 all over 2. And that's our such that in this example is 200. So it would be 200 times 201 all over 2. What do you guys notice about these two? They're the same. So whether you think of Gauss's trick or whether you think of the formula, it's going to be the same thing. N times n plus 1 all over 2. And we end up with, we can reduce the 2 and 200 to be 100. And then we add 2 zeros to that guy. Dun, 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 dun. But that's not the point of this section. If it was, it'd be kind of lame. It's like, why are we just doing series all over again? The point is, can we apply it to something? Can we apply it to the area problem? So you ready? 20,100. Let's talk about the area problem again. So the area problem says, okay, we have this curved region, or a region with some sort of boundary that's a curve. A region with some sort of boundary that's a curve. But it's not circular, and that's the only curve that we've been able to deal with up until this point. We can do circular areas because of the cool number pi and the relationship we learn in geometry with pi r squared, but it's not a circle. There is an example, I believe, on the next page, so I don't want to start writing it if I have it just ready to go. I do. So when they give you some sort of area that they want you to find, the very first thing that you're going to have to do is split the region into rectangles. And to split it into rectangles, we're going to have to take the region A to B, the distance of which would be B minus A. The distance of that interval will be B minus A, so A's x value, B's x value, subtract the 2, that's the distance between them. And we're going to split that region up. And to split that region up, we're going to say, hey, take B minus A and then divide it by n. N being the number of rectangles that you're trying to fit in. So if you're trying to fit in 4 rectangles, you're going to cut that distance into 4. If you're trying to fit in 10 rectangles, cut that distance into 10. So n is going to denote how much we're sectioning, or partitioning is a snazzy math term for it. Partitioning the sub the into. How many subintervals we're partitioning the interval into. And then somehow we have to think about bases and heights and add together the areas. Now a real quick hint about bases and heights before we get to the example. Let me move him down just a little bit. Bases are going to be able to be found by delta x's, which are going to be able to be found by b minus a all over n. Bases are going to be found by delta x's, like how far horizontally you're going to the next subinterval. Because when we split this little guy into, I don't even know what, if we split him up into little regions, then the base of each rectangle is going to be that little delta x, how far in between each of the little endpoints, which will be the same distance as taking the b minus a and splitting it into those n pieces. Those are the bases, little delta x's. The heights, hold on, we know heights. Aren't heights just y values? Go up to the y, go up to the y, go up to the y. So somehow they're going to be special y values, and we'll talk more about that in a little bit. Special y values are special, in this case, function values, because in this case we have y equals f of x. So we could also say special f of x. So bases, little delta x's, heights, little y values. Bless you, bless you. All of this is under step 1. They give you an area and say, oh no, it's not geometric. It's not a triangle. It's not a rectangle. It's not a circle. It's not a trapezoid. It's something else. Okay, fine. So we have to split the region into rectangles. Thinking of the idea of we need to somehow add together these different areas of these different rectangles to approximate the overall region. So let's take this example. Use the 5 rectangles. Oh, hey, they're drawn for us. Go team. Use the 5 rectangles in figure 12.21, that's just in the book, to approximate the area of the region bounded by the graph of. They tell us the function 6 minus x squared. They tell us that we're stopping at the x-axis, and we're going between the lines x equals 0, which is the y-axis, and x equals 2. But if you guys notice, the little pink up here is that region, bounded by the curve, the x-axis, the y-axis, and x equals 2. So let's think about this. We need to think about adding together 5 different rectangles. And just for sake of clarification, or maybe simplification, maybe I should say, to make it a little bit more basic, I'm just going to say, hey, we're looking for 5 rectangles, each with their own areas. And the areas of rectangles are always going to be bases times heights. Can anybody figure out already what each of their bases are going to be? Just by the clues that were given to us. How wide are they? 2/5. How'd you get that? The distance is 2. B minus A, 2 minus 0. The distance is 2, and we're splitting it into how many partitions or how many subintervals? 5. Good. So each one, you can think of it as my base, which is my delta x, is equal to 2 minus 0 cut in 5. So what would we do differently if they said fit 10 rectangles? Divide it by 10. Fit 100 rectangles, divide by 100. But in this one they said divide by 5, sweet. So each one's going to have a width of 2/5, so we can say like a base of 2/5. Now if you get that, go back to the picture and say, where are each of these rectangles? How high are they going? How high are they going? Don't answer it yet, but look at each one. Maybe individually, maybe try to find a pattern. I'm going to take just a quick second to make a number line. You might have no idea why, but hopefully it will become apparent. Did anybody see a pattern as to how high the rectangles go? What stops them? The curve stops them. On what side of each of the rectangles? On the right side. Good. The curve stops them on the right side. So for the rectangle that goes between 0 and 2/5, for the first one, for the first rectangle that goes between 0 and 2/5, how high is it going? Is it hitting at 0 or is it hitting at 2/5? It's hitting at 2/5. So what's my height going to be? F of 2/5. We'll figure that out in a second and come back and plug into the function in just a second, but it's going to hit at 2/5. Now, what about the second rectangle, the one that spans the second subinterval? Where is it going to hit? At 4/5. So then I'm going to need f of 4/5. Has anybody found a pattern? Where's the third rectangle going to hit? The first one's going to hit at 2/5. The second one's going to hit at 4/5. The third one's going to hit at 6/5. The fourth one's going to hit at 8/5. And the fifth one's going to hit at 10/5, which is 2. How did I make this number line? What was I pondering or thinking or using to get there? The x-axis has been split into a region of 2, or a distance of 2 has been split into fifths. And so what was I using to count to go to each of these? My 2/5. So I'm going to have f of 6/5, f of 8/5, f of 10/5. Oh, that's just 2. Sweet. You like? Multiple choices done. All right, so when we plug and chug, ironic timing too. Kiddos, could we go ahead and write out every single one by plugging in F? Wait, why are we plugging into F? I don't get it. What are we trying to get? The y's, the heights. And the only place that we can find the y's or the heights is to plug into the f of x, right? Okay. So then, here's a cool trick, and it makes life a little bit easier. Here's a cool trick, and it makes life a little bit easier. I want to do one big ol' addition problem and add that plus that plus that plus that plus that. But what do you guys notice is in every single term? Sweet! Pull that out. Life just got shorter. Now what's going on? I need to plug in 2/5, plug in 4/5, plug in 6/5, plug it into where? Can your calculator handle a big old string of stuff that's put in? Yeah! So let's go ahead and just write it all out and say, okay, 6 minus who squared? 2/5 squared. Plus 6 minus who squared? 4/5 squared. Plus, you guys see what I'm doing? I'm plugging into my function when I'm supposed to for each of these. I factored out all the 2/5, now I just have to add all these together. But instead of writing it, I'm actually just saying what I need to be doing. I'm going to plug it and chug it all into my calculator. So I could do 6 minus 6/5 squared, 6 minus 8/5 squared, 6 minus 10/5, which would be 2. Whew! Plug and chug it. Plug and chug it. One big old string. Now some of you are like, I think I could do something with a summation here. And yeah, you're actually kind of right. Keep doing what you're doing, and I'll go ahead and ponder maybe with just a couple of you of how could I use a summation to make this easier. Close. Use your index. But yeah, you're right. Now careful. 5. No. Hold on. No, that's okay. That's okay. It's okay. So if someone wants to try the summation and see if we're also right, if it would equal the exact same thing, this would be 6 minus So some of you guys plug that whole thing in. Some of you guys will plug in the summation and be like, sweet, guess what? You're going to do this for 2/5 and this for 4/5 and this for 6/5 and this for, wait a minute. Is it okay to go all the way up to 5, which is 10/5? Yeah, that's where we stopped. What'd you guys get? Hopefully, either way you solved it. $200 and what? Over 25? Did anybody get a decimal equivalent for that? You can do math and then decimal. Math, a little forward arrow, DEC. 8.48. Did anybody do the summation and it matches up? Remember math and then you scroll to the bottom. Is it 9? Is it A? Is it something? It does match up. Go team. Now, here's something cool. This is just an approximate. You guys see how I put area with a little approximation? It's approximately this, which is this. Uh-oh. It could be kids up here, maybe? Anyway, make sure your phone's off. Area is approximately this, which is this. What do you think we actually want? If we're solving, getting into calculus, doing section 12.5, the area problem. Do you think we want actual area or approximate area? Well, that's what this found us. But do you think we actually only want to be stuck with approximate? I don't want to be stuck with approximating. Let's see if maybe by going through the next couple pages we can get to an actual. Rewrite the sum as S of n. Use S of n to complete the table and find the limit. Ooh, wait a minute. Now we're doing limits at infinity of sums? Hold on. This is sounding promising. Not sticking with n equals 5 or n equals 7 or n equals 10. But instead, a limit at infinity. Okay, let's figure out what they're doing. Let's figure out what they're doing. Number 14 doesn't look too familiar, but number 16, doesn't that kind of look like what we were doing? Except we were stopping at 5 and plugging in 5. We were stopping at 5 and plugging in 5. Now, obviously, this is something a little different. It's not exactly what we were doing. It's not the exact same function. And it's going to be a different area as well. But, I think it looks kind of similar. So let's just play around with why on earth or how on earth or what they want us to be doing with these s sub n's, taking limits to infinity. So here we go. This is going to be our s of n. I apologize, I didn't write it. I probably should have. This is your s of n, and this is your s of n. S of n. Okay. How do they want us to rewrite it? Here's the dilemma. We can't really take the limit as n goes to infinity. I mean, I guess we can. But we can't necessarily solve the limit as n goes to infinity unless we have like an actual function with n. And that's what you guys saw at the end of 12.4 homework. It was like, sweet, give me a function of n's and I'll plug in. But the dilemma is right now, what do I do with the I and the sigma? We don't know until we rewrite. Say, wait a minute, hold on, we have this property. We have this property that says, if you can take out anything that's not an I, because the 1 over n squared would actually be what we would call a scalar. And then take whatever's left with the I. Guys, is there one of those highlighted formulas that tells us how to rewrite this guy? Yes. And the highlighted formula says, for the sum of I, you can go back and look at it. It says to go to multiply by n times m plus 1 all over 2. Why is this looking way better than it did a second ago? The sigma is gone. There's only n's and not i's. And then if we just simplify a little bit, is this just section 12.4 now? The limit as n goes to infinity is going to be of n squared plus n all over 2n squared. What's my case? Top wins, bottom wins, or tie? Tie. So what's my limit going to be? 1/2. The ratio of the leading coefficients, which is 1/2 plus or minus. Oh no, but wait, plug in. A positive infinity squared plus positive infinity over, that's all positive over positive, which is positive. It's just 1/2. It's just 1/2. Yeah. It's just 1/2. Now, I know it says to complete the table. I don't actually know what they asked for in the table, but this is the most important part, so it's okay. Ignore the table. I forget what was there. I think it was probably like plug in n is 1, n is 2, n is 5. Go to infinity, and you're like, yay. Infinity is way easier than all the rest. Now, wait, hold on. This thing looks a lot more complicated, right? Number 16. I want to take the limit as n goes to infinity. Hold on. We can pull out, oh, this is just nasty. Maybe I should distribute this guy in. So I'll get I squared over n to the 4th plus 2 over n squared. Is there a property that lets us deal with sigmas separately, like when it's a sigma of a whole thing that we can separate them? Is that a property? So then I can make this the limit as n goes to infinity. Remember, we have to leave the i's in. We're kind of stuck with them inside. But see if this makes sense. If I pull out a 1 over n to the 4th of I squared, and then I pull out a 2 over n squared of, wait, what's left if I pull all them out? Isn't it just a 1? There's a formula for this guy, for I squared. The limit as n goes to infinity. You guys can double check me, keep me honest. I think it's going to be n times n plus 1 times 2n plus 1 all over 6. Double check me. Okay. Plus 2 over n squared times, how do I take a sigma of a constant? times n. So I can do 1 times n. Oh, okay. 1 times n. All right, whatever. We could have left the 2 in and made it 2 times n. That would have worked also. We could have left the 2 in and made it 2 times n. Either way, I end up with, okay, it's time to take the limit as n goes to infinity of n times n plus 1 times 2n plus 1 all over 6n plus 2n all over n squared. Now what, guys? Does anybody notice something really dumb that I did? No one? I rewrote something wrong. The 6 is good. I rewrote something wrong. No one caught it? Well, the 1 became a 1n because of the property the sum of c is c times n. Keep thinking. What happened? What? He should be a 4th. Poor little guy. There we go. There we go. That's a little better. It's a 1n here. Let me do this to make it a little easier. It'll be nicer on your brains. What if I took out the 1 over n squared and left the 2? Does that look nicer for your brains? And this would be 2n. Is that better? I can pull out the 1 over n squared and leave the 2. Okay, and you take a limit now, right? So what happens is n goes to infinity for both of these guys. Now some of you are like, oh, we have to multiply this? That looks awful. Pause. What's the degree of the top if you multiply it all? What's the highest term going to be, or the greatest degree term? It's going to be 2n cubed. If you were to, like the highest one, the biggest one, will be n times 2n, or 2n cubed. Well, who wins, top or bottom? Bottom. Wait, so that's just 0, right? Who wins, top or bottom? Oh my goodness, what's this end up being? Dun, 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 dun. So sometimes it could end up being a constant or a number, and sometimes it could end up being 0. Well, I don't know if it's easy. I'm not sure I'd say easy. But do you guys see, pause. Ow, I did not push that lead back in. That hurt. Did you guys see how we used those formulas I had you highlight earlier? See? We needed it right there, or else we could not have made this jump. And we needed it right here, or else we could not have made that jump. And we needed to make those jumps to take our limits, or else we would have been kind of just screwed and not known what to do. Now, this is all going to come together. Right here. You can find the area exactly by finding the limit of the sum of n rectangles as n approaches infinity. You can find the area exactly by finding the limit of the sum of n rectangles as n approaches infinity. Given a function, given an a and a b as a starting point, given a function, given an a and b as a starting point. As you guys are writing down the formula is kind of hard and complicated unless you see it fleshed out. So let me go ahead and come over here, and I'm going to take this function with this a and this b and apply what that says. Pause. I plug this guy into that formula. I've gotten all the way down to here. Degrees, top, bottom, who wins? 2n cubed over 6n cubed is going to be 1/3. If you can find it in your calculator, this will be the exact answer of the integral from 0 to 1 of x squared dx. Woo! Section 12.5. We'll go over questions tomorrow, kind of a work day for non-APLAC. And we'll start reviewing. Bye, guys.